You ever look up at a giant skyscraper and just wonder, what is actually holding all of that up? Well, it's not magic. It's this incredible symphony of engineering. And right at the heart of it is an unseen hero, a single component that's basically doing two massive jobs at once. So today, we're going to pull back the curtain on the science of beam column steel design. This is the unsung hero that really makes our modern world possible.
So here's what we're going to cover. First up, we'll meet this amazing component that's doing double duty. Then, we're going to learn the basic language of strength. You know, force, stress, all that good stuff. We'll get into all the ways things can fail, bending, twisting, and buckling. Then we'll see how these things get attacked from all sides in the real world, and we'll reveal the one unified equation that solves it all. And finally, we'll walk through the last safety checks that make sure everything is absolutely solid.
Okay, I know this sounds like the start of a bad joke, right? A massive tower of steel and glass and a little plastic ruler you've got in your desk drawer. But the answer to this question actually gets to a really fundamental principle of all structural engineering.
And the answer is a thing called a beam column. It's this structural hybrid, a real workhorse. It's designed to resist being crushed straight down like a column and being bent sideways like a beam. And get this, it often has to do both at the exact same time. It's the key to how both that huge skyscraper and that tiny ruler manage forces. All right, let's dive into our first big topic, the language of strength. Because before we can really get how engineers solve this incredibly complex puzzle, we've got to learn the vocabulary they're using. We have to learn the lingo. So let's start with the absolute basics. Everything, and I mean everything, starts right here with this one concept, force. In engineering, it's really just a simple push or a pull. That's it. Simple, direct, and it's the source of every single challenge a structure is ever going to face. Okay, now let's build on that. A force is just a push, right? But stress is all about how concentrated that push is. Think of it this way. The force from someone standing on snow might be the same, but the pressure from a snowshoe is totally different from the pressure of a stiletto heel. That's stress. It's the force divided by the area it's acting on. So how do we make sure buildings are actually safe? Well, engineers use this philosophy called limit state design. The rule itself is simple. A structure's resistance, its strength, has to be greater than any loads you throw at it. But here's the really brilliant part. To create this huge safety margin, they actually do their calculations with exaggerated loads, while at the same time assuming the material is weaker than it actually is. They are literally designing for a worst-case scenario that will probably never, ever happen. Now that we've got the vocabulary down, let's get into what happens when you actually apply these forces. This is where we start to see the real challenges pop up in bending, twisting, and buckling. Remember our ruler? Hey, if you've got one nearby, go ahead and grab it. You'll notice right away it's super easy to bend it along its thin edge. But now, try to bend it along its wide, flat face. Yeah, it's almost impossible. This simple little action perfectly demonstrates a core concept in beam design. What you're feeling there are the two different axes of a beam. Bending it the hard way, that's called its major axis. That's its strong direction. Bending it the easy way is the minor axis. And the reason for this is something called moment of inertia. Think about it like a figure skater spinning. When they pull their arms in, they spin way faster. When they stretch them out, they slow down because their mass is spread out. Well, it's the same idea. The ruler is stronger on its major axis because more of its material is extended out from the center of that bend. Okay, but here's where things get really tricky. If a beam isn't supported properly along its length and you put a load on it, it can do something totally unexpected. Instead of just bending straight down, it can suddenly twist and kick out sideways. This is called lateral torsional buckling, and it's the sneaky, catastrophic way for a beam to fail that engineers always have to be on the lookout for. You know, life for a beam column in a real building, it isn't simple. It's not just one clean force coming from one direction. The reality is, it's constantly being attacked from multiple sides all at once. So, picture a corner column in a skyscraper. You've got beams connecting to it from two different directions, right? Let's say north-south and east-west. Well, each of those beams is trying to bend that column, and this creates a situation called biaxial bending. It's this incredibly complex stress where the column is being bent around both its strong and its weak axes at the exact same time. So how on earth do you calculate for that? You've got a force trying to crush it, And you have forces trying to bend it in two different directions all at once. Well, you use this, an incredibly elegant formula that combines all of these effects into a single, simple test. This is it. This is the interaction equation. And I know it looks intimidating, but I promise you, it's actually incredibly logical. Let's just break down what each part of this thing is actually doing. So this first piece, CU over CR, that's the column part of the problem. It's just a simple ratio. All it's asking is what percentage of this thing's total crushing strength is being used up by the vertical force that's pushing down on it. Now these next two terms, that's the beam part of the problem. And just like before, they're just ratios. The first one asks, okay, what percentage of its bending strength in the x direction are we using? And the second one asks the exact same thing, but for the y direction. See? This is how we account for that crazy biaxial bending. And this is the magic key to the entire equation. All of those ratios, the crushing part plus the two bending parts, they all have to add up to a number that is less than or equal to 1. You can think of 1 as representing 100% of the member's total capacity. So if the sum is, say, 0.9, you're using 90% of its strength. It's good to go. If it's 1.1, it fails. It's just a simple, powerful pass-fail test. But hold on, we're not quite done yet. Just running that one equation isn't enough. To ensure total structural integrity, an engineer has to check that the beam column passes this test for every single possible way it could fail. And there are 3 critical failure modes they absolutely have to check. First, is the steel itself just strong enough at any given point? That's the cross-section check. Second, will the member as a whole buckle under the combined load? That's the overall member check. And third, will it do that sneaky sideways twist we talked about, that lateral torsional buckling? And here's the bottom line. The engineer has to run that same interaction equation 3 separate times, once for each of those potential ways it could fail. The design has to get a pass, a result less than 1, on all 3 checks. Only then is it considered truly, completely safe. It's an incredibly rigorous process that leaves absolutely no stone unturned. So we've just unpacked the incredible science that keeps our tallest buildings standing strong. It's this whole hidden world of forces, resistances, and these surprisingly elegant equations. And it really makes you wonder, doesn't it? What other invisible engineering is at work all around us, just silently keeping our world from falling apart?